Thank you. Okay, next on the agenda, we have a talk from Mark Sutton from the Department of Physics at McGill University. And one of the big driving forces for the fourth generation synchrotron is the goal to have a very coherent source, increasing coherence by up to, I think, several orders of magnitude. And so a big question that I have, certainly as a user, is, well, what's that coherent source going to do scientifically? So I understand that Mark Sutton is going to give a talk about a technique that actually relies very much on having a highly coherent source, and that's X-ray photon correlation spectroscopy. So I'm going to turn this over to Mark, and we look forward to hearing your description of this methodology, this technique, and how a fourth generation synchrotron could improve the technical capabilities of such experiments. So thanks very much, Mark, for joining us, and we look forward to your talk.
Thank you for the nice introduction. I'm starting to share my screen. Hopefully it's going to work.
Yep, it's working now.
Okay, and you can see my cursor? Okay.
Yes, we can.
Good. So I'm going to talk about X-ray photon correlation spectroscopy. This is sort of quite orthogonal to the talks we've just heard about machines and rings. This is really talking about the technique, but I think it's interesting to consider it's one of the first techniques that took full advantage of coherence and depended almost totally on coherence. And I think one of the interesting historical facts was the whole justification for the APS ring did not mention the word coherence. And yet that's one of the big things that happened after the ring was built is being able to take advantage of coherence, leading to at least two interesting new techniques. One is XPCS, and the other one is coherent diffraction imaging and tychography and things along these lines. So I think this is sort of an example of what to do. I've posted my talk on my website. The website will also be given on the last slide with the conclusions. So this was work over 25 years or 30 years of experience. It's involved lots and lots of collaborators. Let me acknowledge a set of them right at the beginning. Brian Stevenson, Simon Mockery, and Gerhard Grubel, and I guess, are some of the key players starting off to do this XPCS type experiments, and so they deserve special mention. And there's lots of other collaborators across Canada and other various beam lines, and there's a group under Frédéric Levet in France, who we've also been doing a lot of experiments with. And of course, I've had many graduate students and postdocs involved in all of these things. So here's a little bit, here's the outline of my talk. I want to sort of give you an idea of the physics I'm interested in and why we developed the technique. Then I want to spend a certain amount of time trying to explain speckle. And in some sense, it's going to, back when lasers were first invented, basically very quickly they saw everything they tried to do, the light was completely different. Because of coherent, basically almost all coherent images have speckle associated with them. So anytime you have scattering spread over a set of angles, it gets superimposed by the speckle pattern, which can be an annoyance, or as I want to try and explain today, is actually a feature you want to take advantage of. And then I'll talk some of the experiments that we've done, see what the current state is, and see what's happening in the future. And so that's the outline of my talk. Excuse me. So what I'm interested in is material science. I'm interested in how basically the microstructure of materials affects the macroscopic technological properties of what's happening. Back when I was a student, especially when we learned solid state physics, everything was treated as a perfect periodic array of crystals. But in reality, that plays a small effect, except in things like semiconductors and quantum computing and stuff. But microstructure played a very big role. And if you look at something, and this is a picture of TEMs of copper-3 gold, what you see is there's this grain boundary or interface structure, and typically on the length scale of from nanometers to microns, that's why it's called microstructure, because you can see it in a microscope. And the processing history of the material changes the microstructure, and the microstructure controls the properties and therefore changes the properties. So a lot of advanced material science is trying to understand how to control the microstructure of materials in order to get the properties of the materials to do what you want to do. Just the very fact that the properties depend on the history of the sample means it's a non-equilibrium effect. So really, when I talk to physicists, I say I'm interested in non-equilibrium thermodynamic behavior. Just to give you a little bit of an example, let's imagine diffusion. In diffusion, what you're interested in are the fluctuations in the concentration or the composition away from what the equilibrium value is. You're interested in the equilibrium value, but you're interested in how it evolves away from or towards that equilibrium value. And we all, as physicists, know Fick's law. Grad squared of the diffusion equation becomes a Q squared in reciprocal space, which is what we measure with diffraction. And so what we can see is the rate of change of the fluctuations in the material depends on the diffusion, and it depends on Q squared. We can actually solve this linearized diffusion equation very easily, and what we see is that the concentration fluctuations depend exponentially depend exponentially in time. And the time constant is simply the coefficient of the diffusion equation, which is 1 over grad Q squared. So the first point I'd like to make, emphasizing XPCS, is that you, in some sense, by measuring the time constant as a function of reciprocal space value Q, what you get is a Fourier transform of the equation of motion of the system. And if you want to explain behavior of materials, you'd like to do that. The other point I'd like to mention at this point is that we'd like to directly probe the fluctuations and not so much the average structure. So let me now sort of explain speckle. Historically, when we started trying to make coherent beams, basically you can make any beam of light coherent by sufficient collimation. And so we would basically take 5 or 10 micron pieces of our X-ray beams from wigglers and undulators and use that to be the coherent part of the beam. Immediately we would see speckle superimposed on everything. So let's get a quick introduction into what speckle is. So let's imagine we had a disordered set of scatterers. So that's what's in panel A. There's actually a set of diamonds spread out randomly in some small area. If we simply Fourier transform that, what we would see, and square it, we would see the diffraction pattern, which is what you see in panel B. And as a diffraction physicist, I would look at that and say, oh, there's at least 2 important length scales in this system. There's one length scale, which in some sense is determined by the envelope of all what the scattering is, which is sort of given in panel C, and that is typically what we were measuring with X-ray diffraction is the envelope, and that scattering was 2 pi, had a reciprocal space value, which was 2 pi over the size of the individual particles that are scattering. So this sort of measures the particle size, and that's usually what we were interested in, or that's one of the things that we're interested in. But there's also this very rapidly varying diffraction pattern. So that corresponds to a length scale. What length scale is that? That length scale is 2 pi over the size of the diffraction volume that you're trying to study. And when you have lots of speckles associated with the scattering pattern, you can very generally decompose the scattering into the incoherent part, which is what we would normally measure with an incoherent beam, and the coherent part, which is in some sense the speckle pattern. So why? Well, first of all, the conditions for getting that is that the coherent fraction of the diffraction volume of the X-rays in the diffraction volume is a high fraction of the number of X-rays in that diffraction volume. As soon as you do that, you'll see speckle patterns. If you had single crystals, the speckles will basically be the size of the Bragg peaks, and the Bragg peaks will basically have a shape which is 2 pi over the shape of the sample, and in some sense that's partially what's being done with coherent diffraction imaging, is looking at the shapes of Bragg peaks to understand what nanoparticles do. Why am I interested in it? Well, let's now imagine the particles move around. Well, the speckle pattern depends in detail on the exact position of each of the particles. And so if the particles move around, the speckle pattern moves around. And therefore, by measuring the intensities of the speckles as a function of time, one can get interesting information on the motion of what the particles are doing. And here's the start of the system. Way back in 1991, we showed that we could get a coherent beam of X-rays. And if we shone that actually on a crystal, a single crystal of copper-3 gold that had many, many anti-phase domain walls, basically some of the bright peaks were spread out into diffuse scattering. And now again, we see our two length scale diffraction patterns. There's the size of the red spots, which in some sense is 2 pi over the size of the beam, and there's the size of the envelope of the scattering, which is 2 pi over the distance between the domain walls, or the size of the grain boundaries regions, which are creating the scattering in copper-3 gold. So this is just a static pattern. So now it turns out that the coherence conditions are much easier to satisfy at small angles than they are at large angles. But in general, if you have an incoherent diffraction pattern, which is spread over a range of angles, then you will find that when you use a coherent beam, what you will see is that smooth diffraction pattern will be modulated by a speckle pattern. And the only issue is, can you measure the diffraction pattern fast enough so that the fluctuations of the particles don't average away the speckle pattern and you get a smooth thing? Or if the beam, so if it's static enough, you can basically measure the speckle pattern. And so here, what I've done is I've taken a ring of scattering, of isotropic scattering, so every pixel represents here is basically one speckle, and the y-axis is pixels or speckles. And so if you look at the intensity of the X-ray beam as you go up at a given time around the ring, what you see is the intensity fluctuates between the bright spots, which are white, excuse me, and the dark spots, which is the interference pattern of the speckle, is canceling the scattering. Then we just measured it basically about every 2 seconds, I think, is what the data at this ring is. And what you can now see are the fluctuations in the speckles as a function of time. And so now, the question is, how do you analyze that? But you can sort of see there's some time scale associated with this, but it's a very random process. In principle, or in exactly what we're measuring here, is we're looking at the Brownian motion of polystyrene particles diffusing, or gold particles sort of diffusing in a polymer of polystyrene. And so this is basically the Brownian fluctuations of the small particles. Well, how do we analyze that? Well, what we do is we look at the intensity at a given time and correlate it with the intensity at a different time, and we calculate how far apart do the things need to be for the scattering to completely decorrelate. And so that's the intensity-intensity correlation pattern. It turns out that that's related generally for many systems where the Gaussian approximation of thermodynamics is working to be related to the square of what's called the intermediate scattering function, or G1. G1 turns out to be the Fourier transform of the frequency spectrum of what's going on. So the Fourier transform of G1 is basically the spectrum that you would measure in a frequency spectrum. And we measure the square of it, which for an exponentially decaying system is simply a factor of 2 in the time constant. If we Fourier for diffusion, as I showed you before, that exponential decay is what applies, and the time constant is related to the diffusion constant. So basically what we would see for simple-minded linear diffusion is given by an intensity-intensity correlation function, normalized by the average is basically exponentially decays with the diffusion constant. And so by measuring the diffusion constant as a function of time, as a function of Q, the time constant as a function of Q, we get the diffusion constant. But I guess for this non-equilibrium stuff, I'd like to point out one extra thing. We have lots of speckles. And for isotropic scattering, every speckle that has the same magnitude of Q is basically has the same equation of motion. That's what isotropic means. And so we can basically look at many, many, many speckles at a given time. So in some sense, this is a spatial average. And then we can basically look at how the speckles correlate for between two different times. So we can take T1, and we have over 20,000 speckles at T1, and we can take another T2, we have another 20,000 speckles. We can calculate the intensity correlation function, and what we measure is this, what we call a two-time correlation function. So in the left-hand plot here, where we are looking at the gold particles in the polystyrene, which is the data that I was just showing you, if the two times are very close together, the correlation is always very high. If the two times are far away from each other, then the two times the correlation is very low, and that's what's plotted on this color plot here. And we can see that the diagonals of this plot here correspond to equal time differences. And so in equilibrium, we know that the fluctuations don't depend on time, they just depend on the difference in time, which we usually call tau. And so if we see that the scattering and the two-time correlation function like this are parallel to the diagonal, we know the system is at least in steady state, and in many cases we can infer that it's actually in equilibrium. And if we take a cross-section through the diagonal there, we can see the correlation function. Here it's not exponential, but for simple diffusion it would be exponential. And that's what the blue curve is. It's just one simple plot out through this diagonal. But if in equilibrium, we can average over all of these. They're all different measurements, and so then we can get the red line, and that's basically by averaging, and that's what we would do for equilibrium or steady-state systems. As a matter of fact, we use a sophisticated algorithm, and we get the black line that you may or may not be able to see. It's called the multi-tau algorithm, which basically optimizes the signal to noise. But in copper-3 gold, what we did is we quenched the sample through a phase transition, and so now the new ordered phase are growing in domain size, and so the scattering is now changing in time. But if we were to normalize by the instantaneous average, so in some sense we average away the speckle in a single pattern, we get a diffraction pattern, which is like incoherent scattering, and then we can look at how that changes in time, and now we can see that the two-time correlation function is no longer constant along the diagonals. As a matter of fact, we can see that in the system, the fluctuation times are growing as a function of time. And if we take various cross-sections, we can go through that. As a matter of fact, for any given diagonal, anti-diagonal that we take, we get the red curve. That red curve is actually determined by one parameter, which is basically the time, fluctuation time, and the line shape is, for these particular sample, is universal. So that's the power of speckle. With these new MBA lattices, everybody's going to be seeing speckle whenever they're looking at diffuse scattering, and so they need to consider mechanisms by getting rid of it. So one of the mechanisms for getting rid of it is to basically make the beam size so big that the speckles overlap in your detector. So your detector pixels are much, much bigger than your speckles. And basically any mechanism you have to average away the speckles gives you back the normal incoherent scattering. So let's do it in more detail. Let's do a simple system that we understand. And so, which are going to basically look at here, we're looking at polystyrene spheres in the liquid glycerol, which is a very viscous liquid. And so the particles we're dealing with are about 700 angstroms in radius. So if we were to look at the scattering, and then we basically can dissolve various amounts of particles into the beam, and we're going to look at data from about 3% volume fraction to 50% volume fraction. And we're going to put the small angle scattering detector basically where the beam stop is up at the upper right-hand corner here. And so we're just going to look at one quadrant, because then we can see the largest range of Qs, and we're going to use, we know the scattering is symmetric, so the scattering at any of the other the other parts of the four quadrants will be identical to this. So there you can't really quite see the speckle pattern there, because the other way to get rid of the speckle pattern is to average over many, many fluctuations. And so this is the scattering averaged over the full sequence of data that we took, including many, many fluctuations, and there's the reference. So if we were to look at the circular average of that scattering, and here we see it for 4 different concentrations, you would get the normal small angle coherent scattering. So we have very nice spheres, so you can see the airy fringes from the spheres, and the green curve, which is for 3% volume fraction, is basically n times the scattering of each of the particles. As we increase the concentration, the particles start to get correlated with each other, and basically the blue curve occurs at 49% volume fraction. So we know the small angle scattering is the product of 2 terms. One term is the scattering of the particles, and the other term is to do with the structure factor or the correlation between the particles. So if we simply take the green curve excuse me, and divide it into the green curve is a good measure of the independent particle scattering, and divide it into the rest, we can measure the S of Q. And that's what's shown on the left here, on the right. And the black line, which you can see going through all the data, is actually a fit to the Perkins-Yekovich line shape, which is basically the scattering of hard spheres. And you can see we've gone from basically 3% up to 49%, and you can see a build-up of the scattering of the structure factor where the particles begin to interact with each other. We can then look at what the time constant or the effective diffusion constant is as a function of Q, and for independent scattering, like at small volume fractions, we basically just Einstein's and Stokes diffusion theory, we can see the diffusion constant is independent of wave vector. But as we go to higher and higher concentrations, the diffusion constant becomes wave vector dependent. And as a matter of fact, this peak is very slow. The time constant is effectively quite long at the peak of the scattering, and it's just basically measuring the fact that the particles are bumping into each other and can't diffuse around each other. So this slowdown of the change or of the diffusion constant, or the change in the time constant associated with the diffusion, is what causes the narrowing of the frequency spectrum, and that goes by the name of de Gennes narrowing. And so that gives you an idea of the type of systems we can do. Equilibrium is not so. Equilibrium in many systems is already understood, and so it doesn't give you any advantage. But in non-equilibrium systems, we begin to see stuff that we can't see before. The other point I didn't really emphasize that I'd like to is the fact that fluctuations is the mechanism by which a system can evolve from equilibrium. So what happens is, as the thing goes out of equilibrium, some fluctuations cost more free energy than other fluctuations. Those that cost more free energy die away quickly, and the system basically evolves from an equilibrium distribution to a new equilibrium distribution by basically the fact that the fluctuations is really the equilibrium is really the cancellation of fluctuations in opposite directions. So at equilibrium, they exactly cancel, and so the average doesn't change. But if you go away from equilibrium, fluctuations on one side are biased more than the fluctuations going the other way, and so that drives the system to equilibrium. And as far as I know, that explains basically all of the non-equilibrium thermodynamics in material science. Basically, if you formalize that as a set of equations. Since you can go look at the talk later, here's a list of some of the early behavior XPCS measurements, sort of giving you, and I'm going to give you a summary of some of these data. There's a lot more that are now out there, and I haven't actually, this is a little bit out of date. So, One example of looking at interesting equilibrium fluctuations is what happens when you put your particles into a confined channel, where the channel size becomes comparable to the particle size. And so in scattering, that means what we can do is we can see the small angle scattering from the particles, and we can look at the difference in the time constants, or the XPCS fluctuations, when we look perpendicular to the channel and parallel to the channel. And when we do that, we see the correlation functions have different time constants, and we can plot up the different time constants. And so this is an example of how the Dijen narrowing depends on basically the direction the particles are flowing in a channel. We can look at polymer blends. So here we look at the scattering of polymers. We can measure the absolute scattering in the XPCS as well as the time constants. Here are the time constants for various wave vectors. If we look at how the time constants, or the rate constants, which is 1 over the time constant, vary versus q squared, we can see how they change. And when we can model that with the theory of reptation, which is basically because the particle motion is governed by the motion of the polymers, and the polymers in some sense have to move along their chains. They can't move perpendicular to the chain very easily, and that's the idea of reptation. We can actually see capillary waves on thin films. So simply by doing X-ray glancing incidence reflection, we can basically see this diffuse scattering associated with the capillary waves on the surface or between the thin film surfaces. And here's a set of experiments where basically they show that you can measure the time constants of the capillary waves fluctuating thermally on thin films, and you can come up with a theory of how they scale depending on the thickness of the thin films and the properties of the basic thin films. Here is an example that's more at wide angle scattering. Here they're looking basically at near quasi-diffraction peaks from quasi-crystals. So they're sort of like a Bragg peak associated with the scattering from quasi-crystals, and you can look just off the Bragg peak. So this is the thermal diffuse scattering around quasi-crystal peaks. And you can basically measure the time constant as a function of wave vector squared. So the slope of this, again, is diffusion. So this is showing you that the phase-on modes, which are basically the fluctuations of the incommensurability of the quasi-crystals, obey a diffusion equation. Here's an example where you can basically see the structural effects of the antiferromagnetic domains in chromium, and you can basically now do XPCS measurements, which has quite a structure. The interesting fact here is as you lower the temperature, you basically reach a region where they argued in the paper that this is the zero-point motion of the fluctuations of the antiphase domain walls in chromium, which basically get saturated, which you can see at small angle scattering, low temperatures, because that's all that's left. Here's an example where you basically look between the Bragg peaks in this of copper gold in this case, and you can measure the time constants, which are very long. They're minutes and hours long here. And you can basically look at different models of the hopping probabilities for diffusion, and you can get an understanding of how the time constant varies across the Brillouin zone by basically looking here. Here's the copper-3 gold, where you can see the time evolution of the time constants. From each slice, we can basically get a time constant, which we can look at a super universal plot. And so here, we can actually look at how the dynamical scaling affects the fluctuations in the systems rather than just simply the domain size. So this is a test beyond dynamical scaling that was basically allowed by these measurements. There's much more information in the speckle pattern than we've taken advantage of. Here, we were looking at the transition in cobalt as we quenched it from the FCC phase at high temperature to the hexagonal close packed phase at low temperature. And if we look at basically a row of speckles as a function of time, we see these rapid discontinuous changes in the diffraction pattern. We basically measured those fluctuations, and they're consistent with similar things to avalanches and earthquake statistics. And so we can begin to see some of that information. We can see the fact that there's intermediate behavior, and this is an example of a metallic glass, and you can see the fluctuations as a function of time are intermittent. So sometimes they're slow, sometimes they're fast, and you can look at the statistics of how these go by looking at what happens in your two-time correlation function. And one of the problems I've been working on a long time is, can we see critical slowing down and near a first-order phase transition? And here's an example showing that in basically a Heusler-like alloy, where the ordering of the gold and the silver basically is a continuous phase transition. It has a lot of the properties of an Ising model, and we can measure the time constant as a function of angle and as a function of temperature as we follow the thing, and measure the critical exponent of how the ordering happens, and that's described here. Again, there's a lot more information in the speckle pattern. If you measured the highly accurately the 3D speckle diffraction pattern of something, that's what CDI does. You can invert it and find the exact position of everything. Here, we just looked at how do the speckles move across our diffraction pattern. And so what we're seeing in the black arrows here is how far the diffraction pattern moves as a function of time, basically in a stretched sample of rubber. And so you can see that they basically move in the horizontal, and they move out along the direction of stretching. And this is basically showing you the strain pattern associated with the relaxation in rubber. And so that's a whole new set of information that we can get beyond what happens just by measuring time constants. Presently, there are several sets of beamlines, even a new one at the Sirius beamline as talked about by the previous speaker. There's a beamline at ESRS. The one I've been involved highly in is the one Sector 8 at APS. There's one at Spring 8, and Petra is the new DAISY beamline in Germany and Hamburg. They all have a coherent intensity that sort of we use. It's typically about 10 to the 10 photons per second in our mostly coherent beams. There's sort of the ultimate third generation synchrotron was built at NSLS2. It has a factor of 10 more coherence, and so you get about 10 to the 11. But of course, the future is the new multi-band acromats. And just for summary, and we can talk about it after in questions or in the breakout session, here's each of these beamlines has taken the set of feature beamlines to build. Here we have inelastic scattering nanoprobe, very similar to the beamlines at Sirius, and in particular, two of the beamlines are for doing XPCS and coherent X-ray diffraction. Here's what happened. ESRS has just come online with an upgrade, and they also picked a set of beamlines in which to work on. Argonne has picked a set of 8 beamlines in order to design. Here's what they are. Berkeley at ALS is in the process of justifying an MBA upgrade to their lattice, and they've picked these beamlines, which I'm going over fast, but we can go back slowly if there's more time in the questions. And I basically want to summarize what they've done. So they went and asked their user communities what type of beamlines they collected a set of beamlines which they thought were important. And as sort of emphasized a little bit by ALS and APS is the beamlines they picked were things which were taking more full advantage of coherence. I just sort of like to point out, macromolecular crystallography is more dependent on flux than it is on coherence. And not many of the new beamlines are taking advantage of take advantage of the coherence that are happening from these things. They only take advantage of the increase in flux if there is any. Inelastic X-ray scattering also typically doesn't take into account coherence. It's an incoherent type of measurement. And the main reason you win in these two things is you can focus the beam down to a smaller spot because coherence allows you that, and that's really the only gain that you get in these kinds of beamlines. With the new free electron lasers, the issue is how can we do an XPCS? The typical X-ray free electron lasers only give you an X-ray pulse. It's a very short X-ray pulse, 50 to 100 femtoseconds long, only every few tens of milliseconds, like at 100 hertz. So if you just correlated from pulse to pulse, you would get time constants of order milliseconds or tens of milliseconds, which you can also already do at synchrotrons with most of the setups that are there. How can we take advantage of the short pulse structure of the FEL? So we've proposed to use a split X-ray pulse technology, where you basically split the pulse of X-rays into two parts. You time delay one with respect to the other. You let the first pulse scatter off the sample, and you get a speckle pattern, and you get a X-ray pulse scattering off the second pulse. The delayed pulse scatters off it, and you shine the two speckle patterns on the same detector, so you can use a slow detector, and you can separate the pulses from basically femtoseconds up to nanoseconds, and so you can get time constants on that. If the two pulses are very close together, the two speckle patterns are the same and they reinforce. If the two pulses are far apart and the sample changes in between, then the speckle patterns become uncorrelated. And so simply by measuring the correlation of the speckle pattern that you measure with the sum of the two as a function of time, you can again measure these G2 functions that I've been talking about. Here's an example where we didn't have the X-ray beam splitter working. It turns out to split an X-ray beam, especially at 10 and 20 keV, is very difficult, and we're working on techniques to do that currently. Here, we basically looked at the scattering off of liquid gallium and measured the coherence. It's a little tricky to measure the coherence because we don't want to use the full amount of X-rays because that'll heat up our sample. And so actually what we do is we measure very low count rates. Here we looked at count rates from 10 to the minus 3 counts per pixel to 10 to the minus 1 counts per pixel. But because of the coherence, the statistics over many, many pixels deviates from Poisson statistics. And by how far it deviates from Poisson statistics, we can measure how coherent the beam is. And here, what we're showing is you can sort of see in the red curve, or the green curve in particular, that the number of pixels that have two photons deviates from the upper curve, which is what Poisson statistics, and it's in between what the bottom curve gives you, which is what a fully coherent beam. And so here, we've basically we've shown that we can see a static speckle pattern from liquid gallium, which means we can resolve the time constants at the liquid gallium structure peak, so we can resolve that with our X-ray beam, and so we can in principle do XPCS with this two-pulse technique. Detectors are probably increasing the quality of your detectors is even better than increasing the brilliance of your beam. And so I'd like to first of all point out that we've been living on Moore's law, where the speed of computers has been exponentially growing. Just for amusement, let's plot the peak brightness curve for X-ray beams. And you can see it's growing at an even higher and faster rate than that for electronics. The main reason I want to point that out is we can now basically get quality of X-ray beams which cannot take advantage because the electronics is not keeping up. And so we basically are limited often by the electronics and the computing power that we have in order to do these measurements. But we're working on it. There's a new detector coming out from Rugaku, if it's not already out, where we've basically helped develop at the Sector 8 beam line at Chicago, which basically can be run at single photon counting mode at 50 kilohertz. And as a matter of fact, in bunch mode, we can actually get of order 16 patterns with even faster time constants. And so here's the measurement of a silica particle in, I think this is actually liquid water, where the time constant is, if you can read the graph at the bottom here, 100 of order 50 to 100 microseconds. So the first data point here in the red curve occurs at 20 microseconds, and that's basically taking full frames at 50 kilohertz per hour, so we can do that. If we go into this bunch mode, we can take 10 or 20 X-ray patterns at a very fast rate, and then at a much slower rate, we can basically reproduce that. And so the blue curve is when we basically had the timing of each frame to 2.5 microseconds, and we could get some very fast ones and then some very slow ones. And the black curve, we actually got below a microsecond. So with this detector, basically, which is going to be a commercial detector soon, we can measure things down to sub-microsecond time constants. And here, again, you can see the time constant versus Q has a slope of 1 over Q squared. So this is sort of showing that we can measure diffusion at these very fast rates. Even more interesting is we've been working on a detector called the VPIC detector, which is basically vertically integrated circuit electronics. It can run it has an associative memory and runs in an interesting mode, and we actually were able to synchronize the readout of the detector to the pulse structure in 24 bunch mode at the APS, and we could measure independently. We had to average over many pulses, but we could measure the average intensity of each of the bunches in the ring, and basically you can see the comparison of our measurement of the intensity of each of the bunches in the ring. And so basically there we had a framing time of 150 nanoseconds. And so that's a good place to get near the end. So let me sort of make the conclusions first of all about the XPCS. So I started by demonstrating a speckle pattern, a static speckle pattern only, which we took at a Wiggler line at the X25 beam line at NSLS. And I ended by showing basically a static speckle pattern, which was taken in 75 femtoseconds, averaged over many pulses, at the CLS. And so basically that's a nice set of bookmarks of this progress that we've been making in XPCS. And we now have a wavefront splitting split and delay monochromator. As a matter of fact, this weekend we'll be doing experiments at LCLS using it. I wanted to emphasize again the importance of microstructure and heterogeneity in its kinetics and how that is driven by thermal fluctuations and how XPCS can directly measure this kind of stuff. And we can do it both in equilibrium and in non-equilibrium systems. All the new synchrotrons being built should have an XPCS beamline and do, and there's lots of opportunity there. The opportunity for small angle XPCS is fairly well exploited by the current set of beamlines. To me, the most interesting thing is just like wide angle X-ray diffraction has more information about the structure of materials than small angle scattering, wide angle XPCS has much more information than the small angle XPCS that I've mostly shown you so far. The coherence conditions are more stringent for the higher the angles you can go, but we're now getting beams that are coherent enough to do that. The other thing I didn't emphasize, but I'd like to point out, is that these new MDA lattices at the APS and the one that is 100 times more coherent beam than current coherent beams. And the CLS is even more exciting because it's going to be of order 1,000 times brighter than the current beams at the third generation synchrotron. For XPCS, because it's an intensity fluctuation measurement, basically the time constants that we can measure go like the square of the coherence. So with the new upgraded APS, we should be able to go 10 to the 4th times faster, assuming we could get the electronics and the detectors to work that fast. And that would be 1,000,000 times faster time constant at the CLS. And so that actually gets to the point, which we sort of emphasized a little bit with the VPEC detector, is that then we're going to have to synchronize the detectors to the pulse structure of the synchrotron, and we'll be able to actually get information even between pulses by doing these pump probe and average type things. And we should be able to get the sub-picosecond 10 to 100 second resolution even using the XFELs with these very short pulse lengths. And we're just beginning to take full advantage of sort of in between. CDI takes full advantage of the speckle pattern to reconstruct and make a microscope. XPCS just uses a very simple information about how the intensity changes in a given speckle. But there's a lot of information in between these two limits, and we're basically pursuing various techniques for heterodyning to get more interesting time constants and actually access to the phase, as well as looking at higher order correlation functions, which will give us more information of what's going on. And so I think that's a good point to stop. I guess one of the things, I'm looking at my notes that I meant to mention earlier, I did mention it indirectly, is the first time we made our beam coherent, even without a sample, we saw speckle pattern. It turned out to be related to the microstructure of the beryllium windows. It actually was the boron nitride spray on the beryllium windows that was used in order to keep the beryllium windows from oxidizing in these intense X-ray beams. So don't underestimate the amount of impact that will happen because basically the coherence on the optics will lead to speckle patterns unless the optics is of exceptional quality. And so we had to think long and hard and took several tries to redesign our beamline at sector 8 so that we didn't lose any of the brilliance or the coherence along the beam transport. And we think we have a pretty good understanding of how that happens. And so that's probably a good place to stop. And I think that even puts me on time.
Thank you very much, Mark. We are a little bit pressed for time, so what I would ask, are you going to be in the materials breakout session?
Yes, I will.
Excellent. So maybe what we can do is have some of the questions that have come in, maybe those questions can come up as part of the discussion in the materials breakout.
That would be fine.
Excellent. Thank you very much. I'm going to turn things over to Tom Regier now. Tom is the beamline scientist for the SGM beamline here at the CLS. And Tom's going to explain how the breakout session is going to work this morning.
Okay, thanks a lot, Ian. I'm going to share my screen here. Just let me know if you're seeing the presenter view or the slideshow view.
The slideshow view. Okay.
Is that better? Okay. Yeah, so now it's, thanks to everybody. It's your chance to unmute. Not quite yet. Just let me go through a few things first. What we want to do here is run a breakout session where we can gather some information from the user community. We've been trying to do this over the years, and this is a good opportunity for you to share your input with us. So we need your input. As we move forward, we're going to need more input from the user community, and we're going to need more interaction. We'll see how this breakout session works for that. In the past, we've asked for your input through different mechanisms, one of them being the AUM workshop report from 2015, and then last year through the user survey. And in 2015, we heard a lot about the push for in situ instrumentation and investment, a renewed investment in the infrastructure where Canadian leadership is prevalent. So we took that information and we used that to make some decisions for how to upgrade our facility so far. In 2019, we did a survey where we had over 150 responses, and that information is valuable to us, and we use it whenever there's a case to be made for what the user community is asking for. And so in this case now, as we move to look to CLS2, we need to start asking for more information relative to the new machine. So I want to tell you a little bit about what's been going on now. So I was asked by Gianluigi